Design and analysis of algorithms. Assignment help. For any help regarding computer network assignment help, visit https://computernetworkassignmenthelp.com/https://computernetworkassignmenthelp.com. Email support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or call us at +1 678 648 4277. Problem 6-1. Dynamic and bounded hop all pairs shortest paths. This problem explores some extensions of the all pairs shortest paths (APSP) algorithms covered in lecture and in CLRS. All parts of this problem assume non-negative real weights. We assume that the vertices are numbered 1, 2, n. Weighted directed graphs may be used to model communication networks, and shortest distances, shortest path weights, between nodes may be used to suggest routes for messages. However, most communication networks are dynamic, i.e., the weights of edges may change over time. So it is useful to have a way of modifying distance estimates to reflect these changes. A. Give an efficient algorithm that, given a weighted directed graph G equals V, E, W, a correct distance matrix D for G, a corresponding predecessor matrix pi, and a triple I, J, R, where I, J is an element of V and R is a non-negative real, modifies D and pi to reflect the effects of changing Y, J to R. Your algorithm will need to handle three cases: R equals Y, J, RY, J, and RY, J. For each of the cases, analyze your algorithm. Note, your worst case running time for one of these cases may not be better than V3. Solution: the algorithm should behave differently in these three cases. 1. R equals Y, J. No changes are needed, since no shortest path can change. ComputerNetworkAssignmentHelp.com. 2. RY, J. In this case, we may improve the distances for some pairs of vertices. For each pair, x, y, of vertices, x equals y, set. dx, y equals min, dx, I plus or plus dj, y, dx, y. The two terms in the min expression are as follows. The first term is for the case where the new shortest path from x to y contains the edge I, j. The second term is for the case where the new shortest path from x to y does not contain the edge I, j, in which case the shortest path remains unchanged. Note that, in the first case, the values of dx, I and dj, y do not change as a result of this adjustment, because the edge I, j, cannot be included in a shortest path from x to y or a shortest path from j to y. The total time to recalculate d is V2, since we need to consider all pairs of vertices I and j. The total extra space required is 1. To adjust the predecessor matrix pi, we need only consider matrix entries pi x, y, for which we reduce the value of dx, y. For each of these, we consider two cases. If y equals j, then pi x, y equals I, and otherwise pi x, y equals pi j, y. Note that, in this second case, pi j, y does not change as a result of this adjustment, because I, j, does not appear in the shortest path from j to y. The total time to adjust pi is V2, and we need only 1 extra space. ComputerNetworkAssignmentHelp.com. 3. RY, J. In this case, we may worsen the distances for some pairs of nodes. Unfortunately, this seems to require recalculating best distances in parents for all nodes from scratch. D and pi can be recalculated in time V3 using Floyd-Warshall. B. Give an example of a weighted directed graph G equals V, E, W, a distance matrix D, and a triple I, J, R, such that any algorithm that modifies D to reflect the effects of changing Y, J to R must take omega V2 time. Solution: let G be a line graph with n vertices 1, 2, n and edges I plus 1 for all I. Suppose the weights for all these directed edges are 1. All other weights are infinity. Let E equals n 1 1. Then for every j less than j dj, I equals infinity before the modification, but is a positive integer after the modification. That means that omega, n2, entries of D must change. Now suppose that we add a new constraint to the problem, an upper bound of h on the number of hops edges, in the paths we want to consider. More formally, given a weighted digraph G equals v, e, w, and a positive integer h 0 less than or equal to h less than or equal to n minus 1, we would like to produce a distance matrix D giving the shortest distances for at most h hop paths. C. Adapt the Floyd-Warshall algorithm to solve the bounded hop APSP problem. Analyze its complexity in terms of graph parameters and H. Solution. The Floyd-Warshall algorithm introduces intermediate vertices in order, one at a time, in V. executions of an outer loop. See the code on p. 695 of CLRS. Within each execution of this loop, it considers all pairs I, j of vertex numbers. Each such pair requires time O1 because it involves examining and comparing only 3 entries in D. Computer Network Assignment Help.com. When we add the constraint that the complete path must consist of at most h hops, the comparison on line 7 becomes more complicated. It must consider all the different ways of allocating the h hops to the two parts of the path, the part that comes before the new vertex k and the part that comes after k. So, we define dk h to be the weight I, j of a shortest path from vertex I to vertex j for which all intermediate vertices are in the set 1, k with the added constraint that the path consists of at most h hops. dk h I j can now be expressed as Computer Network Assignment Help.com. The total number of subproblems is now O, V3H, and the time required to solve each subproblem is O, H, which means the total runtime of this algorithm is O, V3H2. For the space requirement, while calculating the results for K, we need distance information for K-1 and all values of H, so the space complexity is now O, V2H. D. Adapt the matrix multiplication strategy from section 25.1 to solve the bounded hop APSP problem. Analyze its complexity in terms of graph parameters and H. Try to get logarithmic dependence on H. Solution. In the description in section 25.1, the matrix L, K, contains shortest distances using paths of at most k hops. Specifically, Lk is the shortest distance for AI j path from I to j consisting of at most k hops. Thus, L0 is the matrix with 0 on the main diagonal and infinity everywhere else, and for every k, Lk plus 1 equals Lkw, where the matrix multiplication here uses min and plus instead of the usual plus and times. Our goal is to produce L(H). If H equals 0, then the answer is simply the matrix with zeros on the main diagonal and infinity elsewhere. Now assume H greater than or equal to 1. We cannot use the successive squaring strategy from P 689 to 690 directly, because that would overshoot H if it is not a power of 2. However, we can get the logarithmic dependence on H by using its binary representation. H equals HLHL minus 1 H1. Since H greater than or equal to 1 equals L1 equals L0, we have HL equals 1. Start with L, HL, W equals W. Then for J equals L minus 1, 1, calculate L, HL, HJ, as follows. If HJ equals 0 then L, HL, 2, else L, HL, 2W. The final answer is L, HL, H1.